Hey folks, this is Major Jones here to talk to you about how we're able to implement the address control logic for our LC3. And this is a fairly simple device, but I want to make sure you understand the operation. So it's a piece of combinational logic, and our only objective today is that you're able to understand that truth table, basically how that's constructed for the address control logic. So let's get started. The address control logic, you may recall, is right here. This is a little block kind of inside our memory slash input output subsystem, right? That receives some signals from the LC3 and controls whether or not our memory mapped I/O, whether or not we're reading or writing from memory or reading and writing from an actual input or output device. And so the truth table you see here from the book is in table C.3, and we have three inputs to this piece of control logic, this piece of combinational logic. Those three inputs are the actual address that we're reading or writing to, the enable signal. This is coming from the LC3, which is a 0 when the LC3 says I'm not trying to do any sort of memory operation right now. We're not accessing this subsystem, and it's a 1 when the LC3 is saying I'm trying to access memory or I/O. And we also have the read-write signal. So we'll get to these control signals that the address control logic is producing in a second. What I'll do is kind of bring to your attention the fact that in this truth table here, there are a couple of specific values that we care about, notably the ones for our peripheral registers, the keyboard status register, the keyboard data register, display status register, display data register, and then we have one sort of catch-all group here for every other memory location. You'll notice at this table, it's a little busy. Honestly, I feel like it's kind of unnecessarily so, but perhaps because if mio.en, right, if memory IO enable is a 0, the LC3 is not trying to access memory. So for all of these rows, right, these control signals are basically meaningless. The LC3 is saying it doesn't matter what's happening. I'm not trying to access memory. So it's normal that there's a lot of zeros and X's in these control signals because for each of these rows at least, nothing's happening. And particularly for something like the keyboard data register, which we are going to read but not write, even when the memory IO enable is 1, we're going to read that, but this write, is meaningless. It should never happen really. And so this row also is kind of full of zeros and X's. There's only a couple of places that we really kind of care about the specific values. And so for the keyboard status register, I'll show you. This is one that we may read and or write. So when we are reading to that register, we want to do a couple of things. Number one, we're going to take memory.enable and we're going to make sure this is low. This is a signal that says, are we specifically trying to access the literal memory unit? So you'll notice here in this diagram, mio.en is a signal coming from the LC3 to the address control logic. The control logic sends another enable signal to the actual memory unit to say, hey, are we trying to access something in the physical memory unit or not? And with the keyboard status register, that's not in the actual memory unit, so this should be a 0. N.mux controls this multiplexer here, which is controlling which value, which element is writing to the memory data register. So it's got basically 4 values. The memory unit plus our 3 registers that can be read from. In this case, if we're reading from the KBSR, then KBSR is kind of shorthand for just the value that's passing through the multiplexer. And then I've also got 3 load signals that control whether or not these status registers that can be written are written to. In this case, they're not. But if in this 4th row here, you can see that I'm accessing the keyboard status register. I'm doing a write to that. So in this case, I'm going to activate the load signal for that status register. And you'll see similar things, for the rest of these registers down here. Notably lacking from this truth table and really the diagram is any logic for accessing the processor status register, or I think this should be MCR, the machine control register. Of course, from Unit 3, hopefully you remember that processor status register has our priority bits and our global and interrupt enable and things like that. There are definitely some spots in our control unit that sort of access that directly, which we'll see in the next lesson. But you may recall from Unit 3, such as when we're discussing the interrupt signals or the halt subroutine, there are some code examples that are in the textbook where these registers are referenced directly, and in fact they are given memory addresses, which we talked about in the operating systems lessons. So I'm not sure why they're not here. I think to be complete, they would be, right? There should be a couple extra rows here for how to read and write from these 2 registers if that's trying to be accessed. And I think maybe I've got an exercise where we do that. Just know that that those should probably be there, and for whatever reason they're not, but they follow the same principles. Okay, I think that's all I got. Appreciate your attention, folks. I'll see you next time.